Hi, I want to share with you some stuff I've been playing around with to simulate cells. But it didn't start off like this. I started off wanting to do a fluid simulation using the GPU. I've seen lots of great sort of 3D animations of this. So firstly, I wanted to learn about the SPH algorithm. That stands for Smooth Particle Hydrodynamics, and it's one of the reasonably simple and effective ways of doing fluid simulation. Basically, the simulation keeps track of particles, their mass, size, position and velocity, and at each time step modifies the positions and velocities based on the forces between them. The particles are not meant to be treated literally as droplets of fluid. Rather, you smooth out the particles by representing pressure and density across the volume and then compute the forces on the smoothed out pressures and densities. And if you set the constants correctly and do the maths correctly, you get a very convincing simulation of a fluid. And I struggled at first to find a good introduction to the algorithm. And the best source I found was kind of unusual. It was a paper applying the SPH algorithm to the evolution and distribution of elements within a star, and it explained all the maths in a fairly accessible way and provided some code too. It also explained the leapfrog algorithm, which was new to me. This method is a big improvement on what's called Euler's method. So Euler's method is basically the simple, obvious way of doing things. You basically compute the accelerations, add the accelerations to the velocities, and then add the velocities to the positions, and repeat for each time step. But this method has some instability problems when the forces are changing, and it means you might need to do really short time steps to stop things oscillating wildly out of control. But the leapfrog algorithm is a simple and effective way to run a simulation like this much more accurately with large time steps, so it's faster. So it's basically computing accelerations at the half time step while doing positions and velocities at the full time step, so leapfrogging over each other. So with this help I soon got something basic working, but it was basic. I've realised what I really wanted to do was simulate cells in a multi-cellular organism. I'd long been fascinated by a process called embryogenesis, the method by which an embryo develops from a single cell to form a complete organism. And I was really interested in all the complex signalling, self-organisation and emergent behaviour from a set of rules embedded in each cell. So I could use the SPH algorithm for this, but treat the particles directly as particles. And then I could make them interact in much more complex ways than in a fluid. They could bond with each other, they could signal to each other, they could have different properties. And this is really what's called an agent-based simulation. And after a while I found there was an open source project called PhysiCell, which does this for cells, and it's really capable, and it's used for studying cancer. But I wouldn't learn much by just installing this, and I wanted to teach myself by building something from scratch, seeing what it could do and where it failed. So I started coding, and I initially built something in 3D in Unity, and this was fairly easy to get going, and it gave me a user interface, and it seemed fairly fast to start with. But I didn't like the way my code was so closely tied into the Unity way of doing things. It seemed to stop me doing things efficiently. There was all this overhead of kind of Unity kind of objects and so on. So then I tried using matplotlib in a Jupyter Notebook. I'd done a bit of work with this, Um, the one thing I had to learn was to do animations in the notebook. You can do this, and that was fun. But the frame rate was pretty slow. I'm talking about like 10 frames a second, and it would make it quite hard for me to interact with the mouse. So I was a bit disappointed with using the Jupyter Notebook, but it let me write in Python, which was good. So then I thought of this library called pygame, which is a really kind of fast method for 2D drawing to the screen, and people have written full decent games. So this is really fast, and it will use hardware acceleration. And I thought I'd just continue working in 2D because it would make things much easier to see what's going on. And I could work in Python, and I could structure the code how I wanted without kind of being limited to use Unity type objects and the world hierarchy. So I could separate the rendering of my multicellular world from the simulation code. And this worked really well, as you can see. And it was much easier to add interaction with the mouse, so I could like grab onto cells and pull them around and stuff. And it was all in 2D, but 2D was fine. I learned loads from working in 2D, and it was a small amount of code as well, and it was Python, which I was very familiar with. So now I could write a simple simulation in which cells could divide and could repel each other, and I used a kind of fake gravity. You'll see that in the Unity simulation to make them cluster together. And then I got more ambitious. I thought, can I grow some hair by just starting from scratch with like a chunk of skin? And bear in mind, each cell in these simulations is trying to operate independently, so all the kind of construction occurs from the bottom up. So each cell is running its own set of rules. It's saying, should I start to turn into a hair or a hair follicle? And it sort of randomly might decide to do that, and it will only do so if it's well separated from some other hair. So that just very dark green cell in the middle of the hair is the start, and then cells near that know their location relative to that point, and they will decide what to turn into. Will they be hair, or will they be that sort of those bright green cells that are where you get cell division, which kind of grows the hair and pushes it out. So what we have going on here is all the skin in sort of red and pink is all kind of bonded to itself, so that has some kind of structure to it, and the hair is all bonded to itself. So when the cells differentiated into the hair tissue, they separated their bonds with the skin. I mean, this probably isn't very accurate, but I'm just kind of playing around. So the hair is kind of detached. Cells are dividing in these bright green regions that you can see very clearly now, and they kind of push the hair out. Now this is the state of the art in my program now. It's kind of it all it's got its limitations. So these new hair cells are not bonded to anything, so they kind of come out like bubbles, and the skin sort of falls apart near the edges because this is only 2D and it kind of gets pushed apart. But there's lots of scope here, and I'm pretty encouraged by it. So yeah, I'm going to keep playing around with this, try and run some other simulations, try and make the hair simulation work better and more accurately, and and I'm sharing the code on GitHub if anyone is mad or keen enough to want to have a go themselves. Thanks very much. Bye bye.